Welcome, everyone. Today, I would like to introduce a transformative concept we call compound engineering, the AI native philosophy for building software. At its core, this is a systematic approach designed so that every unit of engineering work makes subsequent units easier rather than harder. This philosophy was born from our experience building Cora, the AI chief of staff, and has been rigorously battle-tested across the Every.to product suite. The promise of compound engineering is to move us beyond simple AI-assisted manual coding and toward a holistic system that learns from every feature, bug fix, and architectural pattern. By adopting this mindset, we ensure that our engineering efforts compound over time, creating a more efficient and intelligent development lifecycle. The entropy problem addresses a fundamental challenge in software development: why traditional codebases inevitably decay. In traditional engineering environments, every new feature equals added complexity. This creates a cycle where codebases become progressively harder to work with over time. Each new piece of functionality requires a complex negotiation with legacy code, leading to significant friction. Often, after 10 years of development, engineering teams find themselves spending more time fighting the existing system than actually building new components. As illustrated by the graph, the ease of development drops sharply as time passes, eventually reaching a point where the code is difficult to understand, modify, and trust. Simply put, most codebases get harder to work with over time because each feature added injects more complexity into the system. The compound solution represents a fundamental shift in our approach, essentially flipping the traditional development dynamic. In the framework of compound engineering, every feature implemented serves to teach the system. We move beyond simple patches to ensure that bug fixes eliminate entire categories of future vulnerabilities. As patterns emerge, they are codified into reusable tools, streamlining all subsequent work. This results in a codebase that consistently gains trust and reliability over time. Looking at the graph, we see that instead of development becoming more difficult as a project scales, the ease of development actually increases exponentially. As the system becomes smarter and faster, we transition from the constant struggle of fighting the system to the strategic advantage of teaching the system. Let's examine the main loop, a self-reinforcing cycle designed to maximize productivity and long-term impact. The framework is divided into 4 distinct phases: plan, work, review, and compound. A key insight of this model is the specific allocation of time. We dedicate 80% of our effort to the thinking side of the loop, the plan and review stages. This heavy investment in strategy and analysis ensures that when we transition to the execution side, which accounts for the remaining 20% of our time, our actions are highly intentional and high leverage. The most critical differentiator in this model is the transition from Step 3 to Step 4. While traditional engineering processes often conclude once a review is finished, this cycle emphasizes that Step 4, compound, is where the real gains accumulate. By systematically compounding our findings and refining our systems, we ensure that the progress from each cycle builds upon the last, leading to exponential growth rather than linear completion. Step 1 in this process shift is recognizing that plans are the new code. It is fundamentally more cost-effective to fix an idea on paper than it is to refactor code later. In this paradigm, the plan serves as the definitive source of truth that AI agents utilize for both generation and validation. There are 4 key actions involved in this step. First, we conduct internal research by analyzing the existing code base to identify relevant patterns. Second, we perform external research to consult framework documentation and best practices. Third, we move into the design phase, where we explicitly define the necessary file changes. Finally, we validate the entire approach to ensure the logic holds firm. This process is executed using the /workflow/plan command. This command orchestrates a specialized team of agents: the repo research analyst, the framework docs researcher, and the spec flow analyzer, to ensure every aspect of the plan is comprehensive and accurate. In Step 2, we move into work and execution. This is the phase where the agent takes the lead on implementation while the developer provides oversight. Visually, you can see how the user leverages multiple agents to drive the output directly into the codebase. The process is built on 3 pillars. It starts with isolation, using Git work trees to maintain a clean, separate environment for the task. Then comes execution, where the agent implements the required changes step by step. Finally, validation ensures stability by running tests, linting, and type checking automatically after every single modification. This entire workflow is triggered by the command /workflow/work and progresses through 4 distinct phases: quick start, execute, quality check, and finally ship. The core philosophy here is one of efficiency and scale. If you have confidence in the initial plan and the robustness of your tests, you no longer need to spend time watching every line of code as it is being written.
Step 3 involves the multi-agent review swarm, a process designed for parallelized code review by specialized autonomous agents. Each agent focuses on a specific critical domain to ensure comprehensive oversight. The Security Sentinel scrutinizes the code for OWASP Top 10 vulnerabilities and injection attacks. Simultaneously, the Architecture Strategist evaluates dependency directions and maintains architectural boundaries. For system efficiency, the Performance Oracle detects issues such as N+1 queries and missing indexes, while the Data Integrity Guardian focuses on migrations and transaction boundaries. This swarm produces a prioritized list of findings, categorized as P1 critical, P2 important, or P3 minor, which facilitates seamless automated resolution. This entire workflow is triggered directly using the command /workflows:/review. Step 4 is where we focus on compound, the essential process of capturing taste. This phase is dedicated to extracting your unique engineering intuition and preferences into the system so the AI truly understands how you build. The workflow follows a structured 3-step process. First, we capture by analyzing what worked and what didn't. Second, we index that information by adding YAML front matter to ensure high findability. Finally, we update the system by integrating these identified patterns directly into cloud.md. As illustrated in the diagram, we take raw inputs, specifically learnings, solutions, and patterns, and feed them through our processing funnel. By executing the command /workflows:/compound, the system spawns agents that automatically extract key solutions and write searchable documentation. This results in 2 critical outputs: continuous system upgrades and a library of searchable docs, ensuring that every project benefits from the accumulated knowledge of the last. Our plugin ecosystem is defined by a structured architecture that balances organizational logic with powerful functional capabilities. At the project root, Claude.md functions as the primary intelligence hub, or the brain of the operation. This is supported by a robust documentation framework, where brainstorms and plans are clearly categorized. Most importantly, institutional memory is systematically archived within the docs/solutions directory, providing a persistent knowledge base for the system. Scaling this intelligence, the ecosystem integrates 26 specialized agents focused on research, design, and review processes. These agents are supported by 23 workflow commands and 13 distinct domain skills, allowing for seamless automation and expertise across various tasks. By housing institutional memory directly within the project structure, we ensure that every solution and insight contributes to the long-term intelligence of the ecosystem. This slide illustrates 2 primary workflows for development: the standard loop and vibe coding. Path A represents the standard loop, which is optimized for production environments. It follows a sequential process starting with a brainstorm workflow to define requirements, moving to a planning phase to establish a blueprint, and finishing with the execution of the work. This structured approach ensures every detail is accounted for before deployment. Path B, or vibe coding, is designed for rapid prototyping and discovery. By utilizing the LFG command, developers can move from an initial concept to a pull request in one swift motion. This is particularly effective for personal projects or feasibility investigations. The ideal strategy is to start with vibe coding to explore and iterate quickly, then transition to standard specifications to build the final solution properly. Let's examine the necessary mindset shifts required to excel in modern software development. We need to transition away from old beliefs that hinder progress and embrace the reality of the current landscape. First, we must move past the idea that code is a form of individual self-expression. In reality, code belongs to the team and the users, Our work should prioritize collective ownership, clarity, and utility over personal style. Next, we should challenge the notion that more typing equates to more learning. While repetition has its place, true proficiency comes from deep understanding rather than just muscle memory. It is the logic and intent behind the code that truly matters. Third, while manual review has historically been seen as essential, it can often function as a bottleneck or a form of gatekeeping. The reality is that automated safety nets provide a more reliable and scalable way to ensure quality and security without slowing down the development cycle. Finally, we must discard the expectation that first attempts should be perfect. In truth, first attempts are often 95% garbage. The goal is to iterate fast, learn from those initial efforts, and refine the solution through continuous improvement. In summary, we must recognize that a system capable of consistently producing high-quality code is far more valuable than any individual piece of code itself.
To successfully integrate AI into our development workflows, we must adopt 3 fundamental beliefs. First, we need to extract our taste by baking our judgment into configuration files, like Claude.md, rather than relying on mental models alone. A good rule of thumb is to spend 50% of our time on features and the other 50% on the system itself. Second, we must trust the process. This involves building robust safety nets through automated tests and monitoring, which allows us to step back from watching every individual action the agent performs. Finally, we must embrace an agent-native environment. We should aim for parity. If a human developer needs to run tests, view logs, or take screenshots to solve a problem, the agent must be empowered with those same capabilities. When the agent operates in the same environment as a developer, its effectiveness increases exponentially. Parallelization is your friend. We are currently shifting into a paradigm where the primary bottleneck is no longer human attention, but compute power. In a traditional human workflow, productivity is inherently serial. A person must complete task 1 before moving to task 2, and task 2 before starting task 3. This sequential nature creates a significant time constraint on complex projects. Contrast this with the agent swarm approach. By leveraging parallelization, we can deploy multiple agents to work on different components of a project simultaneously. In this model, Agent A handles feature 1, Agent B develops feature 2, and Agent C completes documentation, all at the same time. The strategy here is to move execution off local machines and into the cloud, enabling us to command a fleet of virtual workers. By running multiple agents simultaneously, we effectively eliminate the serial delay and maximize the utility of available compute to accelerate development cycles. This roadmap illustrates the maturity levels of AI adoption in software development, detailing the shift from human-centric coding to autonomous system orchestration. At level 0, we begin with traditional manual development, where no AI is utilized. Level 1 introduces chat-based interactions, characterized by a copy-and-paste workflow, where developers use AI to generate snippets and then manually integrate them into their projects. As we progress to level 2, we see the implementation of agentic tools. At this stage, AI is more integrated into the development environment, though it still requires a meticulous line-by-line review of its suggestions. The most significant architectural shift occurs at level 3, the plan-first stage. This is the official starting point for compound engineering. Here, the AI formulates a comprehensive strategy before writing any code, allowing the developer to step back from granular edits and focus exclusively on pull request reviews. Moving toward full autonomy, level 4 represents the transition from idea to PR on a single machine, where a conceptual prompt is automatically converted into a functional pull request. Finally, level 5 reaches the parallel cloud stage. At this level of maturity, engineering teams are commanding a fleet of agents operating across the cloud in parallel, enabling a scale of development and maintenance that far exceeds individual human capacity. Our goal is to ship more value while typing less code. To reach this objective, we must embrace 3 foundational principles. First, taste belongs in systems, not reviews. By embedding our standards directly into our tools and infrastructure, we move beyond subjective manual feedback. Second, plans are the new code. High-level architectural design is now the most critical part of our development process. Third, Every artifact enables the next iteration. Every piece of work we produce should intentionally facilitate the next step in the cycle. I challenge you to start by documenting just one pattern today. This shift is essential for moving from a level 2 gatekeeper to a level 3 reviewer. Ultimately, your output is measured by the problems you solve, not the keystrokes you log.